Hello there everybody. So this is the video about the production of materials that is the first component in the HSC chemistry, and so I'm going to be talking about ethylene today. So let me just clear this up. I'm going to be talking about ethylene today, and as probably a lot of you know, ethylene is a very important compound. It's a very important compound because it's a starting material for a lot of things that you probably use in your day-to-day life. For example, if you use poly bags, when you use poly bags, they started out as ethylene. They started out as ethylene, and they were converted by carrying out a series of chemical reactions, a series of addition reactions, which we will learn later on. They ended up making poly bags. But before we start on all of that, I wanted to introduce you, well, probably a lot of you know what fossil fuels are. And I just wanted to introduce you to the concept. So the thing is, because HSC.point sort of asked some questions regarding this, and the basic problem with fossil fuels is that they're dwindling. We don't have enough of them to last us for a long period of time. And the problem with that is because a lot of our fossil fuels go into energy because you have petrol, you have your kerosene, and all of that stuff goes into making energy because a lot of Australia's energy comes from coal, comes from thermal energy, and that is a problem because we want to use some of that fossil fuel for other uses. For example, for production of ethylene for sake, and so what can we do? So that's why we are looking for other sources of energy. We are looking for other sources of energy. We're looking for example, at solar. So you're looking at solar. You're looking at wind sources, so that we can harness our energy from those sources and leave the fossil fuel for some other use. So we've got all of that. So that's the basic gist of it. So let's start with hydrocarbons. Before we get into all of that ethylene stuff, I want to introduce you that there are three types of hydrocarbons. Now these three types of hydrocarbons are, so you've got alkanes, and then I'm just drawing the line, then you've got alkynes, and then you've got alkenes, and then you've got alkynes. And let me just write there, the mathematical formula that you can work out to find alkanes, alkenes, there's only single L, and alkynes. So alkanes, A-L-K-E-N-E-S, they have CnH2n plus 2. Then you have CnH2n, and then you have CnH2n minus 2. If you cannot already work out the pattern, if you can see, it's very easy to remember because you're going down by 2. So you start off with CnH2n plus 2. Then you subtract the 2 and you go down by 2. So you're left with CnH2n, and then you go by a 2 again, you're left with CnH2n minus 2. How this works is very simple. So for example, I say let n equals 1. If I let n is equal to 1, what I end up with is C1H. 2 times a 1 gives me a 2, and plus a 2 gives me a 4. So I'm left with C1H4, which is the same as saying CH4. Then you also have CnH2n. The way CnH2n works, it's the same way. If I let n equals 1, so if I let n equals 1 once again, I get C1H2. The problem here is there's nothing like CH2 because you can just write this as CH2. The problem is there isn't anything that exists that is like CH2. So we have to start with n equals 2. And when we start with n equals 2, we get C2H4, which is your ethylene, or some people call it ethene, which is perfectly right because the way this works is you get ethene, propene, methylpropbutene, stuff like this. And then you also have CnH2n minus 2. If I let n equals 1 again, I end up having C1H0 because 2 times a 1 is a 2 minus 2. It doesn't make sense. Like some people might say, oh look, let's just say that H doesn't mean anything and you're left with C, that's carbon. Well, no, it doesn't really work like that. You can't really have a 0 here. So let's say we start with n equals 2. If you start with n equals 2, you end up getting C2H4 minus a 2, and so you're left with C2H2. And this is the chemical formula for ethine. and then you have C3H. So it's 2 3 is 6. 6 minus a 4 gives you a, wait a minute, 2 3 is 6. 6 minus 2 leaves you with a 4. So you end up having C3H4 probs, and that is propane. So that is how you work. If you're probably wondering why I'm saying that this is, how can I just figure out which one's methane, which one's ethane, which one's propene, all that sort of stuff, it's very simple. The way it works is if you have a 1, if you have n equals 1, so this is, let's say, n. If n is equal to 1, you put a meth in front of it. If n equals 2, you put a meth, sorry, yeah, if you have a 2, you put eth in front of meth, eth, and then you have prop, and for 4 you have but, and for 5 you have pent, and for 6 you have hex, and for 7 you have hept, inc, and for 8 you have oct, and for 9 you have non, and for 10 you have dec. That is pretty much all you really need in the HSC syllabus. So let's start with alkanes. So you've got methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, decane. You probably, a lot of people, high octane fuel, because octane can be added to normal fuel to increase the performance of the fuel, because probably it combusts more easily and therefore your car has a better performance. So clearing all of that up and moving on. So now I've given you the basic idea of hydrocarbons and all of that stuff. So now we can move on. So the thing is, all of our hydrocarbons come from somewhere, and they come from fossil fuels. So all of your hydrocarbons, they come from fossil fuels. No surprises there. But how do we get specific hydrocarbons? The way we get specific hydrocarbons is through a process known as fractional distillation. Fractional distillation. Probably a lot of people know. A lot of you know what distillation is. Fractional is just a fancy way of saying that you heat it, and then you sort of distill the various components out of it by exploiting their different boiling points. So the way that works is, suppose you have a huge cylinder here, and I heat, let's say, crude oil to, and here I have a crude oil mixture, crude oil. So all of this is crude oil. And what I'm going to do is heat this. So I'm going to apply heat. Let me just give a red color to show heat. So I'm heating this up. And what's going to happen is that I'm going to raise the temperature of this fuel. I'm going to evaporate it sort of by, let's say, if I heat this by 1000 degrees Celsius. Now, what will happen is I will convert all of these into vapor, because all of that evaporates. All of the mixtures of the hydrocarbons, let's say, evaporate at 1000 degrees Celsius. Then I'm going to allow this mixture to go into this big furnace over here. And what's going to happen is, suppose I will have little taps here. So I will have little taps here on different heights. So let's suppose I have a tap at height H1, I have a tap at H2, and a tap at H3, height H3. What is happening is, when fuel enters, it starts evaporating, because it starts rising like water vapor rises, so like steam. So it starts rising up. As it starts rising, because there is no heating inside the furnace, I've heated outside and allowed the fuel to go inside. What's happening is the temperature starts to drop. And for example, if it drops by, let's say, 300 degrees Celsius, so temperature here is 700 degrees Celsius. At 700 degrees Celsius, some amount of it is going to convert into liquid, because that's the boiling point of some of the hydrocarbons. And it's going to evaporate, and it's going to convert into liquid. And so I have some mechanisms, some design over here that allows that liquid to settle and move out of this tap. So I get some of that, some of those hydrocarbons through here. And suppose the temperature drops by another, let's say, 200 degrees Celsius. So I'm here at 500 degrees Celsius. At 500 degrees Celsius, a specific category of hydrocarbons, suppose they convert into liquid, and then they are gonna come out. And similarly here, let's say it stops, it just goes down by 200 degrees Celsius even more. So you're left with 300 degrees Celsius, and a category of those is gonna come out of here. So this is fractional distillation because I've taken a heap of crude oil and then I've distilled into various parts based on the different boiling points. Because as it rises, it gets cooler and cooler because there's no heating inside the furnace, and as it gets cooler, it gets converted into liquid and it comes out of here, out of those taps. And the good thing is, a category of those hydrocarbons are of similar nature. For example, at high temperatures, you generally get your lubricating oil. So you get lubricating oils here. At around 500, you get your kerosene. Over here, you generally get something between 500 and 700. You generally get fuel like diesel, like diesel. Near 400, near 300, you get your petrol. And as you keep going up, you can get different amount category of those compounds. So this is how you work. You start off with crude oil, then you can distill crude oil into lubricating components, into kerosene, into fuel, into diesel, into petrol, and all that sort of stuff. Now comes the interesting part. The interesting part is we want ethylene. But I didn't say ethylene in out of here. But the thing is, we don't need so much of lubricating oil. The thing is, 50% of all of crude oil, 50% of all of crude oil is high molecular mass hydrocarbons. So they are like something like C22, H46, that sort of stuff. So this not all of it is petrol. Some of it is, but more than 50% of it is not. And so how do we get from there to ethylene? Well, there are two ways to get to ethylene. So let me just clear this up, and then we're going to discuss the two ways to get to ethylene. The two ways to get to ethylene from high molecular hydrocarbons, from lubricating oils, because we don't want to use petrol. Because the reason is petrol can be used in your cars. It can be sent directly to petrol industries. We have a lot of lubricating oil. We have a lot of high molecular weight stuff, and so we don't need so much, and we can use that to make ethylene. But how do we do it? The way to do it is the two ways. So you have what is known as catalytic cracking. So you have catalytic cracking, and then you also have something that is known as thermal cracking. So you have catalytic cracking, and then you have thermal cracking. From name, you might be able to tell that this catalytic means it makes use of catalysts. And from thermal, you might be able to tell that it uses basically nothing more than heat. So you heat it all up, and you get stuff. So let's start with thermal cracking. Okay, so I'm just going to create a, oopsies, should have been a better straight line, and here we go, close enough. So let's start with thermal cracking. Thermal cracking is pretty much what you think it is. It is, you just heat it all up, and the temperatures we get up to are like something like, not 1000 really, but something like 700 degrees Celsius. You heat all of that, lubricating oil up again by 700 degrees Celsius, and you keep on breaking it down until you get the desired component. For example, if I start off with this compound C10H22, okay, and I want to convert this to ethylene, and what I'm going to do is heat it to something like 700 degrees Celsius, and I'm going to end up having C8H18 plus C2H4 in the end. And please do remember to write the states in the end. So you start with the gas, you have a gas here, and again you get a gas here. So this is alkane, alkene, alkyne. This is decene. Yep, decene, and this is your octane. This is, yes, because it is CN, so 2 8 16 plus 2 18, so it is, this is octane, and this is your ethylene. So we have taken a large molecular mass. Why is it a large molecular mass? Because let's think about it. I think the molecular mass for carbon, the weight of carbon is, let me just check, I think it is something along, yep, here we go. It is 12.01. So it is 12.01, oopsies, 12.01 times the 10 plus 1.008 times the 22. And when you solve that, it's already 120.1 plus something along the lines of 22 here. So you end up having almost 142 point something. So it is almost 142. So it is a high molecular weight, 142, whereas compared to C2H4, which is of like 2 times, so it is 24 plus something like 4, so it is around 26. So definitely 142 is greater than 26. So we have converted our high molecular mass to a low molecular mass, and that is the essence of thermal cracking. Thermal cracking has also another one category. It is called steam cracking. It is pretty much a category of thermal cracking. What happens in steam cracking is pretty simple. You don't really need to know it, but it is just, you put in your large molecular weight stuff, something like this, into a furnace, and you put steam in at high temperature, and then you heat the steam and this mixture to a high temperature, and you try and get to this, that is the ethylene. So now that we've discussed thermal cracking, the problem with thermal cracking, why do we not use it so much? The reason we don't use thermal cracking so much, it is because it requires a lot of energy to heat something to a 700 degrees Celsius. Like, look at the amount of energy you need to get up to that temperature. So it is really, really high. So you're actually using a lot of fossil fuel. You're using a lot of fossil fuel to make some other compound of fossil fuel, and it's expensive. Energy is expensive. So we don't really fancy this procedure. What we come back to is catalytic cracking. Catalytic cracking, what it does is simply reduce this temperature. We add a catalyst into our furnace. So we add a catalyst into a furnace, and it lowers the activation energy. Catalysts lower the activation energy. Now you might be wondering, what is this fancy term, activation energy? So let me clear this up, and let me explain what catalytic cracking does. So catalytic cracking. Catalytic cracking. So catalytic cracking essentially is you add a catalyst into your hydrocarbon to make the activation energy lower. So just writing here, lowers activation energy. For example, if I need to, suppose the unit of energy is joules, so we measure energy in joules. So just remember that it's like meters, but meters is a unit for distance, and joules is a unit for energy. So, for example, if I want to carry out thermal cracking, maybe I need to invest in something along 10,000 joules. I don't know how much it is, but let's just say it is 10,000 joules hypothetically. If I add in a catalyst, to my reaction, maybe I will not, but I will not have to invest so much energy in order to get to my desired compound. I'll probably need to invest 4,000 joules nest, or even let's say 5,000 joules nest. Let's say I will only have to invest half the amount of energy, and I can still get the desired product. For example, it is simply the same reaction. Again, let's say you have C18H38 in gas. What's going to happen is this is going to get converted into 4CH2 double bond here, CH2. Explain all of this double bond structure to here, and plus C10H22, and this is again a gas, and this is again a gas here. And I have put a catalyst. Also, it is important that you remember that catalyst do not take part in the reaction. That is, if you put a catalyst, so I'm going to put catalyst here. The thing is, catalysts do not affect the product. Catalysts don't combine with your reactant and do not influence, do not come about in the reactor products. So you won't have something catalyst oxide. Suppose you put catalyst as something like sulfuric acid. You're not going to have sulfuric acid reacting with some compound here to give you, like, let's say, hydrogen sulfate or something like that. Sulfuric acid will remain sulfuric acid throughout the reaction. All it is doing is speeding the reaction, the rate of reaction. So let me just write that down. Rate of reaction goes up. So the rate of reaction goes up, and that is essentially your catalytic reacting. Now you might be wondering, what kind of a catalyst is it, and probably how a catalyst works. Well, I'll not give you a detailed amount of information of how a catalyst works, but I'll just give you something that can help you to grasp, to comprehend this concept of catalyst. So let's say so first of all, the catalysts used in the catalytic cracking are actually called zeolites. So zeolites, zeolites, and they are compounds made up of silicon, oxygen, and aluminium. So they are compounds made up of silicon, oxygen, and aluminium. And how they work? Well, I will give you, later on, if you keep on doing chemistry, which I hope you do, you will learn about, the industrial uses of ammonia, on, how important it is. So the thing is, it is made from what is called a Haber process, N2 plus H2, and this is it is a very complex reaction, but essentially, this catalyst, what they do is they have something like a surface. So imagine that this surface is a catalyst surface. This is my catalyst. So this surface is a catalyst. What happens is, if you put in your compound in, So let's say my compound is made up of, let's say, red and part blue. So these are my two atoms combined together, making a compound. And I'm reacting this by some compound that is made up of green, and I need a different color, let's say green and black. Okay, these are my two compounds. I'm just gonna, gray out. These are my two compounds, and I want to react them together. What catalyst does is, well, what happens is these two absorb onto the catalyst surface. Absorb, remember. What happens is this comes onto the catalyst surface, so you have red. The bonds between these two atoms weaken, between two molecules weaken. So red separates from blue, and probably blue goes there. And similarly, you have green coming here and the black going there. So now they're separated. Now that they're separated, the catalyst has already broken down the bonds for you. All you got to do is form a new combination. So you have probably a red combining with a black now, and a green going with the blue. So, and a green going with a blue. So this is how essentially catalyst works. So remember, my textbook definition is catalysts lower the activation energy of the reaction and thus increase the rate of reaction. So they speed the reaction up. However, they do not take part in the reaction. They do not end up becoming something else in the product. If your zeolites remains zeolite, suppose your zeolite is silicon, oxygen, aluminium, that such a compound doesn't exist. Like, suppose it is something like CiOAl, just hypothetical, it does not exist. It says something like this. I've just set on top of mine, and you add it in. It remains that. It does not change. It doesn't end up reacting with your ethene in the end or something like that. It remains like this throughout the reaction. And that's good because, you don't want something else. You're aiming to get this. You don't want it to end up becoming something else, and you've got to have additional costs to separate it. Anyway, now we come to one of the next important parts of our first component of the video, and that is the reaction of alkenes, So let me just change back to like now. So reaction of alkenes. The thing is, this is one of the most important HSC questions that you might pop up sometime. It is, why are alkenes more reactive than alkanes? Why? It's two questions really. Why are alkenes more reactive than alkanes? Or sometimes they might ask, question mark, why is ethylene so reactive? Well, the reason is sometimes you gotta draw the structure. So let's say I will have an alkene structure here, and I'll be drawing an alkene structure here. This is my alkene, this is my alkene. An alkene, I'm gonna draw methane. So I have CH4 it is, so CC. Sorry for my terrible drawing. Just make me one more attempt. CC. Computer is laggy. CC. H here. Another H here. H. So you have C2. Oh, sorry. This is not methane. It is ethane. So you have C2H6 because you got 1, 2, 3, 6 hydrogens and 2 carbons. Similarly, over here, I'm gonna have ethylene, so C2H4. The reason that these hydrogens are sort of bent is because of something called VSEPR, something like that. The reason is because you've got 2 electrons repelling on one electron there. So you get this cluster of hydrogens close together around, see the V shape here, and similarly a V shape here. Now, alkanes are called saturated compounds, and alkenes and alkynes are actually called unsaturated compounds. I hope you see where I'm going. I hope you see where I'm going with this. Saturated. What does saturated mean? Suppose I have a pot of water, or let's say just a glass of water, and there's this water over here, and I add sugar in it. Well, it will dissolve first to 2 teaspoons. If I add, like, let's say 1 ton of sugar, into, let's say, 100 mils of water, well, you're not gonna have all of the 100 mils of water absorbing 1 ton of sugar. So we say that the solution is oversaturated, or that is an oversaturated solution. Or we say the solution is saturated. That is, it cannot take any more of sugar in it. It cannot absorb any more sugar. So no matter how much more sugar you add to it, it will not be effective. You won't have more sugar going in it. It won't absorb. Unsaturated means that you can keep on adding sugar, you can keep on adding stuff, and it will still be okay. So let me just take this off. And get back to, okay. So we say that alkanes are saturated and alkenes are unsaturated. They have got a double bond here, and this double bond can be broken to form a single bond. And if you think about it, if I break this bond, I have one more vacant spot. So I've got hydrogen, and then another vacant spot opens up here, and then I've got similarly hydrogen already here, and a vacant spot opens up here. Because of these two double bonds, alkenes are more reactive than alkanes, and similarly, because of the triple bond in alkynes, they are more reactive than alkene or alkanes. That is a textbook answer to this question, that why are alkenes more reactive than alkanes? Well, alkenes are more reactive than alkanes because they have a double bond in between the carbons, and this double bond makes it unsaturated and therefore has vacant spots. You can add in more You can carry out a variety of reactions, whereas alkanes are saturated, they don't have any more space left in them, to accept or to carry out any sort of reactions. However, you can carry a substitution reaction in which one of the hydrogen goes off and you add something up here, but we'll discuss that later. But end of story is this is more reactive because you have a double bond here, and this does not, it is saturated, you can't add more stuff in. This is unsaturated and you can add more stuff in. Now we're going to talk about the reactions that you can carry out with alkenes. So the reactions that you can carry out with alkenes are, the first reaction is called hydrogenation. The first reaction is called hydrogenation. What it simply means is addition of hydrogen. So for example, I have hydrogen here and I'm going to react it with my ethylene to give me. So what will happen? What do you think? Let's think, like, the problem, these problems can easily be simplified with structures. So I'm just going to make H2 because it's simple. And there I have two carbons, and I'm sorry, double bond here, and a hydrogen, hydrogen, hydrogen here, hydrogen here, hydrogen here, and another hydrogen here. What's happening? Well, simply this bond is going to break. So let's break that bond and add another vacant spot here. So now we have added hydrogen, hydrogen was already there, this hydrogen, and similarly another two hydrogens already there. But now you have two vacant spots, and what's going to happen is one hydrogen atom from the hydrogen gas over here is going to go. So let me just say this. One of those hydrogens is going to go here. One of those hydrogen atoms is going to go here. And so this is your hydrogen, this is your ethylene, ends up having C2H6, which is ethane. So you have converted ethylene to ethane by simple addition of hydrogen, because you're adding it. You're not replacing anything here. You're not doing anything. You're simply breaking down this double bond and adding more atoms. And there you have. You've converted ethylene to ethane by simple addition of hydrogen. The next reaction in this category is halogenation. Halogenation is simply addition of halogens. So halogens are like the bromine. For example, I'm going to say CHC2H4, yes, plus bromine gas, Br2. And let's just say this, and let's just say this. What's going to happen? Well, let's draw the structure again, shall we? So you have C2 double bonds here, hydrogen, 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 hydrogen. I'm going to draw hydrogens here, but you get the gist because there are four lines. There's four hydrogens here, here, here. And then you're going to have bromine and bromine. What's going to happen? Well, just let's break this double bond for a start, and you're left with this. Well, now the two hydrogens were already here, so these two hydrogens were already here. So you have a hydrogen already there. Nothing's going to happen to those, but you have two vacant spots. And here you've got two bromine atoms, and there you go. One bromine goes here, one bromine goes here, and you end up having something like C2H4Br2, right? And that's it. That's all it is. Let me ask you a question. Can you carry out this reaction with CH4? Well, it turns out, let's say it's hard because the thing is, it is saturated. Where is the place to add another bromine atoms? All of those have already been taken up by hydrogen. So it is relatively hard unless you do something, expose it to UV light, I guess. Maybe it will end up reacting because you're adding more energy to it, and some atomic structures, they reassemble and carry out reaction. That is some other, there's a special case, but the gist is these can easily react, these cannot. So now that we have covered halogenation, let's move on to the next one. The next one is very easy, and the next one is hydrohalogen. Hydrohalogylation. What is this? Well, this is simply addition of hydrogen halides. So what are those? Well, those are something like hydrogen compounds like HCl, hydrogen bromide. Those are hydrogen halides. So let's draw this again. So C2H4, that is your ethylene, in a gaseous state, reacting with HCl, again in a gaseous state. What does this give you? Let's draw the structure again. C, double bond in between, hydrogens all around, 4 hydrogens, and HCl. Remember, this is I don't know if you know, but this is a dipole, as far as I remember, because it's more electronegative. Never mind. Don't confuse yourself with this, but that was just off the top of my head fact. So let's break that double bond for a start again. So let's break the double bond. Now you have those 2 double bonds were already there. So let's make them first. But now again you have 2 vacant spots. One here and one here. Let's fill those spots up. So first hydrogens and hydrogens were already there. That's okay. Let's take this hydrogen and put it here. Let's take this chlorine and put it here. And similarly, you can also do this sort of reaction with hydrogen bromide. Put the hydrogen here or here, whatever you prefer, and put the bromine here. And this is your hydrohalogenation, so pretty easy, right? And please don't remember to put the states up, so it ends up becoming C2. How many hydrogens? 1, 2, 3, 4. C2H4. Oh, actually, there are, sorry. C2, 1, 2, 3, 4, 5. C2H5Cl. There you go. I will give you a nomenclature video in which how to write these properly. But now I just want you to get the gist of it. In the next video, I'll explain the nomenclature, and then you will be able to write them just like the way they're written in textbooks. And now we have come to our last reaction. We're clearing this all up. The last reaction is called addition of water, so hydration. Now it is pretty self-explanatory, but it is simply, so you've again got C2H4 reacting with water. The thing is, here you've got to remember that you add a catalyst, and that catalyst is something you probably already know, sulfuric acid. And I remember this does not have to be concentrated, this can be dilute. And I'll leave you to think about it for a second or two, and I'll explain why this doesn't have to be concentrated. And this ends up becoming, so let's think about it again. So this ends up giving you ethanol, C2H5OH, right? The thing is, so you've got CC again over here plus water molecule looks something like this. What ends up happening is, so let's draw our basic structure again. There. So let's say the water molecule divides into hydrogen plus the hydroxyl group, it is called. This is called hydroxyl group. Don't need to worry about it, because when you study ethanol later on, you'll get really experts on this. But what ends up happening is it ends up splitting into hydrogen and a hydroxyl group. So let's say that hydrogen, so let's just put our standard hydrogens here. So you had a hydrogen here for the starters. Now let's say I will take this hydrogen and put it up here, and I will take this hydroxyl group and put it up here, and there you go, you have C2H5OH, your ethanol. Now the answer to the question which I asked earlier, why does this have to be dilute and not concentrated? Turns out it makes sense, because ethylene over here, our friend over here, has a double bond. That means it is already highly reactive. That means this reaction already does not require a large amount of energy. And catalysts, they don't have to do so much work. So we can do with the dilute sulfuric acid and get our desired product, which is ethanol. And later on you will study how we can convert the ethanol to ethylene, and there you will require concentrated, because here you see you don't have any double bond, so you require more energy. So you require more energy to carry out that particular reaction. So with that being said, it's also important to note that ethylene can also undergo oxidation, and polymerization. Oxidation is not really that important in the HSC, but it is ends up making something a sort of antifreeze in cars, which is used, but nothing really to worry about there. But what is very important to note before I leave this video is that you can carry out polymerization reactions with ethylene. You can make polymers, and I will explain what polymers are, but that's just a sneak peek to my next video. So hope you enjoyed it, hope you understood it. If you have any questions, I will leave my email address down there. You can send me emails. Hopefully I will try and answer them, or you can just leave them in the comments down below. And have a good one. See you guys.